In the last session, we had learnt about the basic ideas of permutation test. In this session, we would see another resampling technique called the cross validation. Cross validation is a way of measuring the predictive performance of a statistical model. So, we would be learning what is the basic idea of cross validation and some of the variants of cross validation, and then we would see how we can implement cross validation in R using the boot package. Cross validation is a way of measuring the predictive performance of a statistical model. Now, generally model fit statistics like R square does not necessarily mean how good a model will predict. It says given the model how good is the fit, and one can tweak the R square values by introducing more and more explanatory variable. That is, it is easy to overfit the data by including many degrees of freedom, and then it inflates the R square value. For example, take a simple polynomial regression. If we go on increasing higher order or go on adding higher order terms, go on increasing the power of the explanatory variable, the fit gets better and better with increase in R square, but that does not essentially guarantee that the prediction would be best. So, higher R square is not necessarily a good measure of prediction. Now, one way to measure the predictive ability of the model is to test it on a set of data which has not been used for estimation. Now, this happens. Now, how can we do this? We can take the data and divide it into two sets. One set is called the test set and one set is called the training set. For the training set, or the training set is used to fit the model, while the test set is used to see how the prediction happens. So, the fitted model is applied on the test set, and so for the test set we have a set of observed and the set of predicted values from the training data, and from there we can have a comparison of, or we can judge how the predictions are happening. Now, accuracy can be predicted, or the predictive accuracy of the model can be measured using the MAC on the test set. Now, note that generally MAC of the training data is less than MAC of the test data, because the training data is used to develop the model. So, there the mean square error would be lesser, but the question is, what is the division that needs to be made? We are having a data and we need to divide it into two groups. So, what is the length of each group? Sometimes it may so happen that there is not enough data to allow some of it, or at least a substantial part of it, to be kept back. So, here comes the idea of leave one out cross validation, which we say as LOOCV, in which the accuracy measures are obtained using the following algorithm. Now, assume that there are n independent observations y1 to yn. Remove observation I from the test set and fit the model using the remaining data. Then we can calculate the error EI star, which is yi, or EI hat, which is yi minus yi hat for the omitted observation. Now, EI hat is obviously the predicted residual, and we repeat this step for 1 to n. Then from E1 hat to En hat we calculate the MAC, and this is called the CV, or the cross validation. Now, note that this has a striking resemblance with the jackknife procedure, where the statistic is computed leaving one observation out, and then that is repeated for all the observations. Now, this is a efficient use of the available data, because we are using the entire data set barring from one observation at each step. But if n is large, then this can be time consuming to implement. So, a variant of cross validation is leave k out cross validation, where instead of 1, k observations are left out at each step. And there is another technique called the k-fold cross validation, where the original sample is randomly partitioned into k subsamples and 1 is left out in each iteration, having a similarity with the idea of blocked bootstrap. Now, minimizing a CV is a useful way to do model selection, and it has many applications. For example, variable selection in context to regression, or choosing the number of degrees of freedom for a non-parametric smoother. But the only caveat is that if we are doing a statistical test after selecting variables using cross validation, the test do not account of the variable selection that has been taken place, and the p values can be misleading. So, it is more of the prediction purpose than the model fitting purpose is cross validation used. Now, another problem with cross validation is that a small change in the data can cause a large change in the model select. Now, to avoid that, researchers have found that k-fold cross validation works better in this respect. Now, we had said that for general models, cross validation can be time consuming to implement, because we have to implement the same procedure repeatedly for all the keeping out one at a time all the n observations. However, the advantage for linear models is that we have a direct formula to calculate the leave one out cross validation estimator. So, if we assume a linear model of the form y is equal to x beta plus epsilon, then beta hat is x prime x inverse x prime y, while the fitted values y hat is hy, which is x prime x inverse x prime y. So, the matrix H, which is x prime x inverse x prime, or x transpose x inverse x transpose, prime or transpose being the same, is called the hat matrix, and the diagonal values of hat matrix. So, if we denote the diagonal values of hat matrix as h1 to hn, and we had used them for external bootstrap also, then the cross validation statistics is given by CV is 1 by n summation I runs from 1 to n ei by 1 minus hi, where ei is the residual obtained from fitting the model with all observations. Cross validation for time series. So, when data are not independent, cross validation becomes a bit difficult, as leaving out one observation does not remove the entire association due to correlation with other observations. So, for time series forecasting, a cross validation statistic is obtained as follows. Let the data be y1 to yt, and let yt plus 1 hat denote the forecast of the next observation. We compute epsilon hat t plus 1, which is yt plus 1 minus y hat t plus 1 for the forecast. Now, we repeat this, changing t from m to n minus 1, where m is the minimum number of observations needed for fitting the model, and then we have epsilon hat m plus 1 to epsilon hat n, and we can compute the MAC, which would give the CV in case of time series. The CV can be well implemented using many functions in R. So, there are a lot of packages which implements different variants of cross validation. Here we would just be showing a couple of cross validation using the boot package. So, we first call in the library boot to load the package. We would be using as an example the mammals data from package mass, So, library boot, and we fit a GLM which is mammals.glm, log brain explained by log body, data equal to mammals. Note that the facility in boot package which is called cv.glm performs the cross validation in context to GLM models, but model that we have fitted here is a LM model or a linear model, but that can also be fitted using GLM without specifying the family and the link option. So, the default family and the link option makes the GLM to be a linear model. So, we just fit this, and then we say CV1 is CV.glm, the GLM object. So, the data is mammals and the GLM object. So, if we run this and then use the command names the CV.glm object. So, here it is CV1. So, it is call, k, delta and sit. It is the errors are stored in the delta object. So, we can just to see the errors we can use CV1 $delta, and it gives two values 0.4918 and 0.4916. So, the first component is the raw cross validation estimate of the prediction error, and the second component is the adjusted cross validation estimate, with the adjustment being designed to compensate for the bias introduced by not using leave one out cross validation. And here, since we have used that, we find that both the values are nearly same. Now, we can use the direct formula for linear models to compute this. So, we introduce mu hat, which is fitted mammals dot glm, that is the fitted object, and then mammals dot diag is glm dot diag mammals dot glm. Now, the glm dot diag is also a utility function in the boot package which calculates jackknife deviance residuals, standardized deviance residuals, standardized Pearson residuals, the Cook statistics, leverage and estimated dispersion. And we are interested in this leverages, which are the H or the diagonals of the hat matrix. So, we define CV.err from formula which is mean of the fit residuals, mean of the observed minus the fitted, that is the residual square, by 1 minus the H squares. And the moment we do it, we see that this value is exactly equal to the first output of CV1 $delta, which is the raw MAC values. Now, to perform the k-fold, to perform the k-fold cross validation, we can use the cv.glm command, but with an extra additional argument which is a capital K, and then if we say that, for example, if we want to do a 10-fold, we get cv error.k, which is again 0.4926402. So, here we have done a k-fold cross validation. In this session, we have learnt about the CV or the cross validation technique, which can be used to assess the predictive power of a model. So, now we started with the resampling technique. We have learnt about jackknife, we have seen the theoretical aspects of bootstrap, we have seen the practical aspects of bootstrap and how we can use R to implement different variants of bootstrap for different statistical problems. Then we have learnt a basic idea about permutation tests, and today we learnt about the cross validation technique. In the next session, we would be providing a general recap on all these methods and conclude the session on resampling.